All right, so we are in section 15.3. We're continuing our work with double integrals. We're going to now do double integrals over general regions. So what we talked about in the last section, every one of our regions had a projected region down into the XY plane, or whatever plane it was in projected into. The base surface was a rectangle. So now we're going to say, what if that's not the case? So for example, maybe you have something where in three-dimensional space, you got your surface floating up here, doing whatever it's doing, and then projected down into the XY plane, maybe it's this region, actually, maybe it's almost the exact same region projected down into the XY plane. So the question is, what if D is not a rectangle? And how are we going to handle that? So that's what we're going to talk about during this section. All right, so we want to evaluate the double integral of x plus 2y, so that's our surface, dA, so over the region, excuse me, over the area projected down into the xy plane, if D is between the curves y equals 2x squared and y equals 1 plus x squared. So first thing we should probably do is go ahead and sketch what these look like. So let's see, y equals 2x squared. Basically, that's just your parabola. It is going to be centered at the origin, and it's going to be a little wider than normal. So it'll look something like that. It's going to be y equals 2x squared. And then we're also going to have y equals 1 plus x squared. And 1 plus x squared is basically going to be a parabola which is shifted up 1 unit. And these two things will intersect. So it's going to go through 1. And then it's also going to open up. And these two things are going to intersect. Now, I didn't draw this really to scale very well, but you get the idea. Y equals 1 plus x squared. That will probably intersect at slightly higher values than this, but it's okay. So what we're talking about is this region right here. So that's the projected region down in the xy plane. Y, x. So whatever our surface is doing, we want to know what the volume is going to be between the surface and that specific region in the xy plane. So in order to do that, we're going to need a few things. First of all, we're going to need to figure out where the bounds are. So I'm going to need to figure out, see where these two things meet. So we're going to set 2x squared equal to 1 plus x squared, so we can at least figure out what the x values are. So let's see, we'll subtract x squared on both sides. We get that x squared equals 1. Square root on both sides, we get that x equals plus or minus 1. So we have our x bounds. So the question is, how are we going to set this thing up? I know it's going to have to be a double integral. And notice it's very non-specific. It says dA. Well, that means we have to kind of figure out which order this thing goes in. And I'll explain what I mean by the order in a second here. So what we're going to do is we're going to do what is called a type 1. This is what we're going to do. It's going to be a type 1 double integral, or type 1 region, to do our double integral. And a type 1 region means that the functions are going to be from top to bottom. Or another way to think about it is we're going to do the double integral of f of xy dy dx. And as I set it up, I'll explain what I mean by top to bottom and why it's dy dx as opposed to dx dy, as opposed to that order. So the idea is this. When we do these double integrals, we're trying to find the volume. Whatever the outside most integral is, needs to be all constants. So the outside integral, which in this case is going to be dx, because that's what I put up here, is the outside integral, needs to be constants. Well, we know what x goes from. It goes from -1 to 1. Here's the -1, here's the +1. The y part is going to vary from function to function. So y is actually going to vary from here, oops, I meant to change the color, from here to there. So when I set up the dy part, I'm going to go from the bottom function, which is 2x squared, to the top function, which is 1 plus x squared. So it's a top to bottom type thing. We're actually going to go from the bottom to the top when we evaluate it. But really what we're doing is we're ultimately taking the difference between the top and the bottom function. And then our f of xy in this case is our x plus 2y. So when you set these up, because it's dy dx, and this is what's considered a type 1 region, that means the y's will vary from function to function, and the x's will vary from a constant to a constant. And the reason you need the constants on the outside is because if you have functions on the outside, considering you do the inside integral first, you're going to end up with a function of another variable at the end, and that doesn't do us any good. We're trying to find the actual numerical value of this function, of this volume, excuse me. So now we can go ahead and evaluate this thing. So remember, we're taking the antiderivative with respect to y first. So we're going to get, we're going to get xy plus y squared, and we're going to evaluate that from 2x squared to 1 plus x squared. Don't forget, we still have the additional integral of dx to do later. All right, so now we're going to go ahead and we're going to substitute this stuff in. The algebra on these gets to be a little lengthy sometimes. There will be a one or two that I'm going to show you a slight little shortcut and a couple of tricks to look forward to, but for the most part, you just got to plug this stuff in and go with it. So we're going to plug in 1 plus x squared for each y. So I get x times 1 plus x squared plus 1 plus x squared squared minus plugging in the 2x squared. Now I'm going to get 2x squared times x, so that's 2x cubed, and then 2x squared squared is going to be 4x to the 4th. And then again, don't forget, we've still got dx and our second integral. Now you're most likely going to want to go ahead and expand all this stuff out, combine like terms, just to make sure it's easier to take the next antiderivative with respect to x. But now we do have everything in terms of one variable, so now it just basically becomes your standard single integral. So let's go ahead and expand all this. So the first one's going to give us x plus x cubed. 1 plus x squared squared will be 1 plus 2x squared plus x to the 4th. And then we're going to subtract 2x cubed and 4x to the 4th. And then after all that, we're still going to have to take another integral. So let's combine all these like terms the best that we can here. So it looks like I've got a minus 4x to the 4th and an x to the 4th. So that's minus 3x to the 4th. Okay, I'm done with those. Let's see, minus 2x cubed and x cubed is minus x cubed. Done with those. Just got one of the x squareds there, so I got 2x squared, an x, and a 1. All right, now we can go ahead and take the integral from -1 to 1 of that function dx. All right, so let's see what we get. Negative 3/5 x to the 5th minus 1/4 x to the 4th plus 2/3 x cubed plus 1/2 x squared plus x from -1 to 1. Fortunately, these are ones and negative ones, not too horrible to deal with. All right, so let's see. We're going to plug in 1, so we're going to get negative 3/5 minus 1/4 plus 2/3 plus 1/2 plus 1 minus, now be careful plugging in the -1, Normally, if you plug -1 into an odd power, it's going to make it negative. If you plug it into an even power, it's going to make it keep whatever the sign is. For example, plugging -1 into the x to the fifth gives me -1 times the -3/5, so it really makes it a positive 3/5. But plugging the -1 into the x to the fourth makes that +1 times the -1/4, so it keeps that sign right there. So the next one will be -2/3 plus 1/2 minus 1. All right, so let's see what we can get rid of here. -1/4 minus -1/4, those are going to go away. 1/2 minus 1/2, those are going to go away. Nothing else is going to go away. So let's go ahead and combine what like terms we can. So we're going to have -6/5, 2/3 minus -2/3, so +4/3, and +2. So it looks like we're going to have to put everything in terms of 15ths here. So that's going to be -18/15 plus 20/15 plus 30/15. So -18 and 20 is 2, plus 30 is 32/15. And that's our volume. Again, not a very short problem when it comes right down to it. So this will most likely be several videos. I'm going to say at least 3, I think, because these problems just take a long time to do. Okay, not horrible, though. Once you set it up and once you get it rolling, you just got to be careful on all of your algebra. All right, that was a type 1 region. So now we're going to evaluate the double integral e to the x over y dA if the domain is given to us as y varying from 1 to 2, x is going to vary from y to y cubed. Okay, so they kind of give us the bounds. If we didn't know the bounds, we would probably have to figure out where the domain of the region was by projecting it. But since they gave us the bounds, there's not really much we have to do. This one, as you can tell, however, the y values are the ones that vary from a constant to a constant, and the x's go from a function to a function. So this one is considered to be a type 2 region. That's supposed to be a 2. There we go, type 2 region. And that's going to be something which varies from left to right. So the double integral would be a double integral over d of f of x, y, and this one's going to be dx dy. And again, the easiest way to think about that is the outside one, the dy here, has to be the constants, because you have to finish with constants. Otherwise, you're still going to have variables left over in your integral. Most of the time, it won't work out very nicely anyway. So let's go ahead and set up our double integral. So the double integral, we know that y is going to go from 1 to 2. X is going to vary from y to y cubed. Our function is e to the x over y. And again, this has to be dx dy. Okay, so in order to take this antiderivative, let's see, we have to do this with respect to x first. So this could be done with a u substitution. However, you don't necessarily need to. If you recall, way back in calculus ABBC, Calc 1, Calc 2, if I had e to the 2x and I wanted to take the antiderivative of that, the antiderivative would be e to the 2x times the reciprocal of the slope of the composite 2x there, which is 1/2. That was kind of a shortcut to doing the entire u substitution process. Well, this basically can be done in the same way. If I were to think about x over y as being the same thing as x times 1 over y, actually I should probably write it as 1 over y times x, it's the same thing. So when I take the antiderivative of e raised to that power with respect to x, it's just going to be e to the 1 over y times x times the reciprocal of that slope, which is going to be the reciprocal of 1 over y. So the antiderivative there would end up being a y e to the x over y. So that's what we're going to get for our antiderivative here. So we're going to get y e to the x over y. If you need to do the u substitution, by all means go ahead and do so. Just remember you're doing this with respect to x, so treat y as a constant. We're going to evaluate that from y to y cubed. So let's see, plugging in y cubed for x is going to give me y e to the y cubed over y, which is y squared, minus, and if I plug in the y, I'm going to get y e to the y over y, which is e to the 1, or just ye. And now we can take antiderivatives with respect to y. Now in this one, we actually do have to do a u substitution. Technically, we need to probably split these integrals. So let's go ahead and do that. So we're going to take the integral from -1 to 1 of y e to the y squared dy minus the integral of y e dy. And it's the first integral we have to use the u substitution on. So we're going to say that u is y squared, du is going to be 2y dy, or dy is du over 2y. And again, this is just in reference to that first integral. So let's see, we're going to get y e to the u times du over 2y. I'm going to go ahead and change the bounds. You don't have to do it this way, but I feel like it might be easier. I'm not sure. Let's find out. So if I plug in -1, I'm going to get out 1. If I plug in +1, I'm going to get out 1. Well, hey, that actually works out very, very nicely. And then in the second one, I can actually just take the antiderivative with respect to y. Remember, the e is a constant. I technically could have pulled that out to the front. So I'm really just going to get 1/2 e y squared, and we'll evaluate that from -1 to 1. Now, why is the first one so nice? I've got an integral from 1 to 1. It's going to give me 0. All right, there shouldn't be anything left, assuming I did that correctly. And I'm pretty sure that I did. I'll still show that, that cancels out with that. And then you would just be taking the integral of 1/2 e to the u from 1 to 1. But either way, it should end up giving you 0. So that should be 0 minus. Plugging in 1 for y, we're going to get 1/2 e minus. Plugging in -1 for y, we're also going to get 1/2 e. Okay, and I knew something wasn't right here. It just took me a second to figure it out. For whatever reason, I completely started changing my bounds. So let me go back and correct that. I don't know why I started writing 1s on the top. That should actually be 2. So that should be 2. That should be 2. Hopefully you caught that well before I did. That should be 2. And then this one over here, it is going to change. So plugging in the -1 still gives me 1 on the bottom, but it's now going to give me 4 on top. So that definitely changes this whole thing. All right, let's fix this. So now we are going to actually have to do this. So this will be 1/2 integral from 1 to 4 of e to the u du minus, I have gone ahead and done this one right here. So that's going to be 1/2 e squared, e to the y, no, sorry, ey squared from -1 to 2. On the left-hand side here, we are going to get 1/2 e to the u from 1 to 4 minus 1/2 ey squared from -1 to 2. So now let's see what we end up with. So if we plug in 4 into the first one, we get 1/2 e to the 4th. Plugging in a 1, I get minus 1/2 e minus. Plugging in a 2, I am going to get, let's see, it's going to be 2 squared is 4, half of that is 2, so I get 2e. Plugging in 1, we get minus 1 half e. Hopefully this all looks right. I think it does. So what's going to go away? It looks like this minus 1 half e minus a minus 1 half e. Those are going to go, oops, that's supposed to be red. These are going to go away. And then it leaves me with 1 half e to the 4th minus 2e. So there's your volume doing a type 2. And obviously we had to use a couple of antiderivative techniques, use substitutions and so on. All right, I think I'm going to stop the video here on this one. Like I said, this will most likely be at least a three video lesson. So I'll probably do like 3 more examples and then probably the last 3 examples in the third video, or last 4 examples in the third video.